I want to start talking about some examples today of how to use the standard solutions and solve some of the find a harmonic function things that we built last time. I'm going to get the rest of the notes typed up. I've started already, and then I'm going to give you guys homework exercises, which I'll write up tonight too. You'll be in position to solve some things. So it'll be a mixture of a couple of questions about circle inversion, and then some questions about using the ideas that we've studied in here. And I've actually got a Mathematica notebook that I put together for some of these things, and I found an absolutely beautiful website that illustrates how ideal flows work for airfoils. So I can't go super deep into some of these ideas, but at least I can indicate that they exist. If you're, I think there's at least one aero student in here. So this probably won't be super exciting, but should I put this on video? My impression of looking at the solution to the development of airfoils, which I haven't looked at in a couple years, reminded me how ad hoc it all is, right? It's like, oh look, conformal maps can give you these shapes that look like airfoils, but it doesn't work in math the way it does in real life, so just start blobbing on error terms until it does what it's supposed to, is kind of how the theory goes. So at least we'll be able to see where the idea came from originally. Okay. All right, so last time I think we talked about we set up one ideal flow. So we set up an ideal fluid flow on the upper half plane. And this is just one. There's many, right? There's this. We found one. And we said, okay, well, if you had some infinite sheet of some lazy river crawling along an upper half plane, then one function that you might write down that is a harmonic function that runs parallel to the boundary is this one. So to each point, assign to each point the vector alpha 0. So v of xy is equal to alpha, 0, where alpha is velocity. Speed, really. Right, the magnitude velocity vector. Yep.
So there's a pretty well-known solution in fluid mechanics that says near a surface the fluid flow is going to kind of fall off in no condition, and there's going to be a solution for the velocity profile near there.
Sure.
If it's turbulent, it's like a time average. If it's laminar, it's like actually an exact solution.
Yep.
If you put that profile in there for some thickness, let's say you know what the structure there is going to be, when you transform that into another shape, is the boundary layer going to stay?
It depends on how you set it up, really. If you have an analytic solution, it will carry through as you pull back, yeah. Right? So basically the thrust of the question is the following idea, and so we'll come back to this. This is one solution, this is one flow, right? That doesn't really represent the way things work in physical reality, because you have the interaction between whatever's flowing and the boundary of where it's flowing, right? In physical setting, that actually they interact with each other. So one thing that turns out to be true, so let me finish building the solution real quick, and then we'll talk about what would happen if I had another solution that described a different part of physical reality, right? Or like some piece that described some other characteristic that I want it to be true. This is, I think, the gradient of the function u of x. It's terrible. So this is the gradient of the function u xy is equal to alpha x. So that's our sort of harmonic function. This is our harmonic function that describes this field. And so that means the complex potential here, so u is equal to the real part of the function alpha z. So that's one proof that u is harmonic. If you can exhibit that a function is the real part of an analytic function, then it is a harmonic function. It pretty obviously runs parallel to the boundary. So our complex potential here is f of z is equal to alpha z, which is alpha x plus I alpha y. Remember that the complex potential tells you not only about equipotential lines, but also where the streamlines for the function are, right? That the function and its harmonic conjugate dictate both equal lines of equal potential, right? So this level curves of u, and the flow lines, which come from the level curves of v. Okay. So one feature that harmonic functions have is that if you take if u1 is harmonic and u2 is harmonic, then linear combinations of u1 and u2 remain harmonic. And the reason that's true is because the differential equation we solve to get harmonic functions is a linear differential equation. So linear combinations of solutions to Laplace's equation remain solutions to Laplace's equation. So one thing that's going to come up that we're not really going to get much into in here, but goes to Reese's question is, if you have one flow, for example, the way this comes up in practice is, you might have one flow that describes what happens away from the boundary, and a different one that talks about what happens near the boundary but falls away as you get away. You can take those two solutions and add them to each other to get both sets of behavior in the same field, right? And so the fact that you can do this, that you can layer different flows together, is of sort of real importance in why this is a useful approach to understanding physical situations. Because the behavior that you want to measure, if you can do it with a harmonic function, you just pile them all up and get the sort of sum behavior that you're after. Okay. So he was asking specifically like what happens in here. That's a complicated question that's way beyond the scope of what I could talk about. But if you had a solution that described what happened near here, and you conformally mapped both parts of the solution to a new region, then you would carry both solutions to the new region that you were looking at. If it was analytic, if it was some sort of numerically constructed nightmare, which is often the case in actual engineering problems, is you have a numerically constructed nightmare solution, then you have to rebuild your numerically constructed nightmare solution in the new setting. Okay, so what interesting thing could we do with this? Well, the idea is, if I had a different scenario that I was trying to understand the streamlines for, and I could transform it into that one, I could compose with a conformal map and pull the streamlines that I got here into the new setting, and it would help me analyze what's going on in the setting I'm actually interested in. So what I'm going to try to do is I'm going to start with a problem. I'm going to transform it into this problem, solve it here, and then build a function that will solve the scenario that I'm actually interested in. So now I get to write down one of my favorite conformal transforms. So let's think about a domain that looks like this. So you go along until you get to -1, and then you do half of a unit circle, and then you stop at 1, and then you continue. So you got half a cylinder, okay, I'm going to say cylinder here, half a disk. The way oftentimes this gets talked about in the literature is you're thinking about this as a cross-section of a cylinder. Now we would expect, the expectation here is that how would fluid flow around this thing? Your sort of intuition should guide you to believe it probably comes in and does something like this, right? And then maybe the further away you get, the less impact the cylinder has on the flow of the fluid around it. But that's just a guess. So what we're going to do is we're going to write down a conformal transform that takes this setting to that one. And it's a hilarious conformal transform because I want you guys to tell me why it works. Okay. So I'm going to take this and I'm going to act on it by the map z goes to z plus 1 over z. Okay. What does that do to something that's bigger than 1 on the real line? Let's suppose that x is bigger than 1. Let's see. If x is bigger than 1, what's that? X is, yeah, so imagine here that z is equal to, what I'm going to try to do is I'm going to try to see what this does to things on the real line, right? So yeah, I should say z bigger than 1. So z is equal to x plus I times 0, and the x component is larger than 1. It may be useful when we're thinking about this to think of this map as r e to the I theta plus 1 over r e to the minus I theta. So you put in 2, what number comes out? 2.5, right? Put in 3, 3 1/3, right? So put in 1, what comes out? 2. So it sure looks like this sends this chunk of the real axis to the real axis starting at 2, right? This piece right here that began at this part looks like it got sent to, here's 2. That piece looks like it got sent there. In fact, you can do this. This is a question I'm going to ask you guys, is to show me that this works, right? So I'm going to kind of I'm going to show it, I'm going to tell you what's happening, and I want you to walk through the argument that does it as a homework exercise. What does the circle do? Well, let's see. If I take r to the I theta, the I to the, if I'm on the unit circle, what's the radius? 1, right? So if I took a point on the unit circle, so now suppose I'm here, every point on that has coordinates e to the I theta. What happens if I take a point e to the I theta and I add it to e to the minus I theta? Oops, erased my construction picture here. So imagine you start in a circle, e to the I theta is right here, e to the minus I theta is down here, but if this is x plus iy, then this is x minus iy. I mean, there's sines and cosines running around in the background here. So you end up right there. If you take this point and that point and you add them, oh, let's actually just compute one real quick as an example. Yeah, so let's actually just pick one. So e to the I pi over 3, which is cosine of pi over 3 plus I times the sine of pi over 3, which is, yeah, there was the 2 that I dropped there, which is
1 plus 1.
seriously? 1/2 plus root 3 over 2i and e to the minus I pi over 3? 1/2 minus root 3 over 2i, and if you add those together, you get 1, right? Because you're just adding the imaginary parts canceling, you're doubling the real parts. That's actually why you end up from -2 and 2 here, right? So that point that was on the unit circle, this point right here, got mapped here. And in fact, that's going to be true, right? If you add something on the unit circle to its complex conjugate, then you just double the x coordinate, right? Because this argument will hold for any angle. And so that circle gets squished flat between 2 and -2. And then the negative axis from 1, well, if you put -1 into this thing, you get -1 plus -1, which is -2. If you put in -3, you get -3 plus -1/3, which is -3 1/3. And so you should believe that that yellow region goes this way. So this is a conformal transform that takes that region, the boundary, to this one. Where does 0 get sent? That's not actually a very useful question. So let's see where basically we're trying to track the interior here. So you know what? I'm having you guys do this. I'm just going to assert that this is true. This is a map to the upper half plane. You can do that by checking a single point. See where the interior went. So the conformal map z plus 1 over z takes that the cylindrical sort of half circle with the rest of the line closed off and its upper part of the complex plane, and it maps it to the half plane. So how can I use that? The idea now is that I know the solution. So these things are connected by z plus 1 over z. I know a harmonic function that has a flow in this setting, right? A harmonic function that has a flow in this setting is, we said u is equal to alpha x, right? That's our sort of harmonic solution that gave us this. So let's give this the name h for half plane. And why not put the extra stick on it so it's extra fancy? So u takes the upper half plane to the real numbers. If I call this map T, is there a way I can chain this together to make a map that goes from, we will call this set W for weird. So this is the domain W. Here, I'll put extra stick on it just to be weird. Can you write down a map that takes the weird set to R that is harmonic, built out of the pieces that we have here, and uses this U that we've got? Can I chain these together somehow? Suppose that I start with a point over here. Right? So you start with some point W, inside of W. I want to come up with a function that is a harmonic function that takes points in this domain to the real numbers. Yeah? So I actually would start, since I'm starting with a W here, right? I'm going to start with W, and then I'm going to send it to T of W. This lived in the set W. This lives in the set H. And then U sends H to R. Right? U does this map. My harmonic function U takes there's a flow on this half plane, right? So if you actually compose these functions, you get something that takes W to R. This is a composition, right? First you do T, then you do U. So if you wrote down the function phi is equal to U composed with T, T takes you from the weird set into H, U takes you from H to R, and so we think about this for a second. Now, if there's questions about what I'm doing here, I want them to be clear now, because this idea of starting in a domain, conformally mapping it, and then applying a harmonic function, this is the standard technique here. I have a known solution in an easy setting. I can conformally transform that domain to somewhere else, and so I can compose those pieces together. That's all that's happening here. I'm making the domain different by precomposing with a conformal transform. Yep.
How does the length scaling not hurt? Because that path over the cylinder is like longer. Or sorry, no, it's shorter than that path.
So there's a known transform of metric that happens in conformal transforms. Like you can just track what the distance is. And normally when you're doing this, if all that you're interested in is the streamlines, then the actual you still get this transform of velocities, but that can be modified with the use of an integrating factor if you want to change the.
So you get the streamlines, but your velocities at each point.
The velocities aren't necessarily. It certainly won't be constant anymore, right? Because you're going to get what the scaling factor is going to do is going to induce stretches in the vectors, which means that the particular flow correlated with uniform flow is one distribution of velocities in the image picture. Because the distortion of the gradient field is how you're going to pick up those changes in magnitude. Okay, so I've got a thing, the one thing that we need to make clear about this is that if T is conformal and U is harmonic, then U composed with T remains harmonic. This is essentially a proof by the chain rule that this holds, right? But the idea, this is one of the, again, harmonic functions have all these magic properties. This is another one. If you start with a harmonic function and you conformally transform the domain, you remain a conformal transform. Essentially, that's an assertion that conformal maps interact very well with Laplace's equation.
So, if I wanted to go the other way, which would be more useful.
Then you actually need to know the inverse of the transform, right? And typically, this actually has, this is called the, okay, does anybody actually know the name of this? This is a standard name. Jarakowski transform, I think maybe. This is like the standard sort of conformal transform that's used to begin talking about the way that circles transform into planes in fluids. Right? So yeah, this has a pretty easy to write down inverse transform. So what do we get out when we do this? Well, we get an explicit solution here. Over here, the solution was U is equal to alpha x. I lift that up to an f, which is f of z, which is alpha z. I run it through this. So I have U was alpha x. It had complex potential f of z is equal to alpha z. So then I take f of t of z, which gets me alpha times z plus 1 over z. This thing is the complex potential in this setting. And so if I want to compute the harmonic function that works here, what is it? This is a complex potential. What's the relationship between complex potentials and harmonic functions? The real and imaginary part, right? So if you actually compute alpha times x plus iy plus 1 over x plus iy, this is where the math gets irritating. And you sort this into its real and imaginary parts, you end up with alpha times it's x minus x over x squared plus y squared plus I times alpha times y minus y over x squared plus y squared. So if you do the algebra, you get this sort of real and imaginary part sort. So all I've done here is I put in the transform, so I've composed in the conformal transform. I wrote x plus iy for the z's. I've done the algebra to sort it into its real and imaginary parts. And this function right here, this is what determines the streamlines in this, or this is the harmonic function that gets me the equipotentials in this picture. So this function we'll call phi. And what phi does is it gives you these guys. So these are places where phi is constant. So these are the level surfaces of that function. And the level surfaces of this function, which is psi, gives you the streamlines. So the psi function, if you look at places where it is constant, you get these lines. So this is where psi is constant.
So you get the stream function for free.
The stream function comes for free. This is the whole point here, is there was no differential equation to solve. Doing this transform gave you not only the equipotentials or level curves of your solution. This is the harmonic function that has the right boundary conditions. It's a harmonic function that has the right boundary conditions. It induces level curves by setting it equal to constants. So this is each one of these is a set of x's and y's that make these lines have constant value when you plug them into U. Remember the gradient field, if you calculated the gradient field for this, it would be the gradients are perpendicular to these things. So every time that you calculate the gradient, you end up with something that's perpendicular to the level curves of phi. And then the streamlines are the things that go through those in sort of an orthogonal way. And those are the level curves of the harmonic conjugate, which you got for free from the complex potential. So this is kind of like the basic picture here. You have some known solution and some conformal domain that lets you map back and forth. And then if you can understand what's happening here and you can trace through what goes on with the conformal map, then you end up with a picture that looks like this. Okay, so how did the early progenitors of the study of airfoils use this tool? So there's a couple of different ways you can do it. You can play with more complicated versions of this. So this is actually a special case of a much more complicated map that's got quadratic terms, those terms that are raised to some power between 1 and 2. Or instead of transforming a sort of half of a circle centered to the origin, it turns out if you take that circle and you slide the center of it slightly to the side, the transforms of these circles, actually going to pull this up on my computer in a second, the transforms of circles that are not centered at the origin turn into shapes that look like this. And so this picture, right, this is where the early people that worked out like how wings should work, this is how they did it.
That transform.
This transform, this one,
That's not at the origin.
yes, does
so
this.
what, you composing the
What you have to do is you have to require that the circle continues to pass through the point at 1, 0. So there's you impose this condition that it continues to pass through this point.
But I'm just wondering how you practically use that, because you still want to start with a half-plane. So then you go through this transform to this circle, then you go through this another transform.
Yeah, you basically do a transform that takes your okay. Okay, this is not a sort of in the weeds thing. This is a real question. How would you use this to generate more complicated shapes, right? So if you could get yourself a unit circle, you could do this, right? If you could get yourself a unit circle, you could play this game. So what you do is you say, okay, well, what if you started with a circle that went through the point 1, 0, but was centered somewhere else? So let's really like wildly exaggerate here. Let's put a circle that runs out here somewhere, maybe with this center. It's not really the center of the circle, so maybe we'll put it right here. Right? So you have a circle that doesn't, it's not going to look right. But what you can do is you can take that circle and you can transform it into this one, because all you're doing is reduce the radius to 1 and shift the center and then reduce the radius to 1. That's an easy transform, right? And then once you do that, then you can apply this map to get you to, it's like the, this direction is the direction z plus 1 over z. That gets you this picture. Or sorry, not that picture. What am I doing? Z plus 1 over z takes you from here to here. So you can start with a circle that's shifted off, put another conformal map in, and then use the standard map. And if you go the other direction, if you start with this, and you play with where that center is, and you look at the shape that comes out when you do that, you end up with some really bizarre transforms. Yep.
It's just pass through 1, 0, not -1 all.
Just 1, 0, yeah. So it's one condition. So let me actually show you guys what that looks like. See if my computer will let me do this. Okay, don't disconnect, don't disconnect, don't disconnect. Mathematica notebook I made for the next part. So the next thing that we can talk about is, so all of this stuff was basically using a boundary condition that du dn was equal to 0. Right? The boundary condition that we imposed here was a Neumann condition, a very simple one, but it says that the flow runs parallel to the boundary. It doesn't cross the boundary. So these are all Neumann problems. Right? But we haven't really talked about what you do with the Dirichlet problem. So in an earlier class, we talked about the Poisson formula, which was that god-awful looking integral that said that if you told me that you were on a disk and you gave me some sort of conditions that said, suppose this is the unit disk, and you tell me that u of you prescribe u on the boundary. You prescribe u on t. That is, you tell me the boundary values, and as long as u is continuous, then there's this integral formula against the Poisson kernel that tells you what the harmonic function is that has that, right? So u of z turned out to be equal to the Poisson integral. And that's a really useful tool, right? You give me some values on the boundary, you hit it with the Poisson integral, you get the function in the middle. Unfortunately, that integral is often extremely difficult to compute. If you remember the formula that I wrote down, like it's not something you're going to be analytically do oftentimes. It has to be integrated numerically. And so there's a simpler, so this is one of the standard models here, right? So this is a standard solution. If you could turn a problem into a disk problem, then you can solve it using the Poisson integral. And so that means anything you can conformally map into a disk, you can recover off the harmonic function idea from before. So this is one of our standard solutions for a Dirichlet problem. Dirichlet. Remember, in a Dirichlet problem, it's the boundary values that are prescribed, not the derivative on the boundary. But there's a better one that shows up in the sort of simplified examples that we often use, which is a half-plane solution. Half-planes are the best planes. So there's what's called the half-plane standard solution. And that's built off of a picture that looks like this. So the goal is going to be to find a harmonic function that has these boundary conditions. It's defined on the upper half plane, and the boundary conditions are over here, the function is equal to 1. And over here, the function is equal to 0. And I want to find a harmonic u on the upper half plane. Yep.
So can harmonic functions be non-one-to-one on their domain, or is it only on the boundary?
It's the boundary.
Okay.
I mean, at least locally, right? If you think about harmonic function as sort of like, I mean, you've got a two-dimensional set going into a one-dimensional set, right? So the one-to-oneness is not even a thing you can even make sense of, right? The analytic function associated with it, though, analytic functions at least locally are one-to-one, right? There are going to be issues with branch cuts that show up in this one. So it turns out to be the case that I'm going to write the solution down, and I want you to convince yourselves it's a solution. So I'm going to make the following claim. If I put a point z is equal to x plus I y right here, and I measure that angle right there, which we'll call theta. And theta has a name, by the way. It's called the argument of z. Right? That this angle turns out to be that you can write down this function. U is equal to 1 over pi times theta. So my argument is that's a harmonic function and it has the right conditions at the boundary. What's that?
That's like pi like the number.
It's what? Yeah, that's pi like the number. Yep. Just a number. Just a constant. That's there actually to impose the right conditions at the boundary. So, claim 1, that's harmonic.
So you just pick u so that it has some action in the plane, but would you really care about those things?
Yeah, so to exhibit that this is harmonic is really easy. It's the fact that it recovers the right boundary behavior that's going to be the thing that we really care about here. So, first question. This thing is the real part of an analytic function. Is there an analytic function you know that has the argument living inside of it? Log, right? What was the definition of log z? Log z was equal to ln of z. In fact, let's write log r for right now. You know what? Never mind. I lied. Ln, so log z is equal to ln of r plus I times the argument of z. Right? That's kind of that was the definition of the log, right? Well, the thing we wrote down is not the real part of that, it's the imaginary part of it. So maybe I can fix it. So you notice that this is almost what we want because theta is equal to the argument of z in this picture. So it's almost what we want. And so the way that we're going to fix it is we're going to write, well, if this function is analytic, is this one? If I take an analytic function multiplied by a constant, does it remain analytic? The answer is yes. So 1 over pi I log z is going to be equal to 1 over pi times the argument of z plus 1 over pi I times the natural log of the radius. So that guy right there, that's the real part of an analytic function. So u is the real part of an analytic function, and so it's harmonic. So u, 1 over pi theta, is the real part of the function 1 over pi I times the logarithm of z. Where we're going to choose log to have a branch cut that's like running down into the lower half plane somewhere to make sure that we stay away, they keep the branch cut away from the upper half plane. So if you're the real part of an analytic function, you are harmonic. Condition 1 met. I'll leave condition. I hear the bell ringing. So condition 2 is this function has the right behavior as you hit the boundary with it. So that's something to think about. And the next thing to think about, which I'll talk about next time, is how we take this solution and we build it up so that we can prescribe as many intervals as we want with fixed temperature. So we can think of this as sort of being a discrete version of the Poisson integral is kind of what we're doing here. And then this is going to be the entrance to our study of how heat type equations are solved instead. So I'm going to post some homework based on sort of earlier stuff, and then once we get the heat stuff, I'll add some more questions. So, all right, see you guys.